In this video, we're going to introduce a process called separation of variables. We've already looked at visual techniques for solving equations, differential equations. We've also looked at approximation techniques, Euler's method, for generating a graph a little mechanically with straight line approximations. All of these are a little unsatisfying because there's no exact answer provided. However, the nice side is that you don't have to do any calculus to build those solutions. Even if they are approximate, we do less complicated work. However, we would really like to have a calculus-based technique to actually get a formula for y equals with some x's in there. That would be our ultimate goal. Let's start off with our basic equation for exponential growth that we've seen before and ask ourselves, how could we start here and solve it in a systematic way as to get y equals? The key element of this is to treat the dx and dy as separable units, thinking them as delta x and delta y. And then we'll see what that plays out with as we manipulate this equation. We start with dy dx equals k times y. And our goal is to, as it says in the title here, separate the variables. We're going to take this dx here, and we'll bring it up to the other side. We'll take this y, and we'll move it down to the other side. And the k we could move or keep, it doesn't matter. Usually it's easier just to leave things where they are if they don't need to be disturbed. So here, we'd end up with 1 over y, bring the y down, dy equals k times dx. Now we've seen this kind of formulation before in integration by parts. This is not really that helpful by itself, but what it turns it into a helpful form is adding an integral sign in front of each term, in front of each side. Now this is perfect. This is something we can interpret, and notice that this is y's with no x's. This side here has x's, has k's, but the key thing is there's no y's involved. That has achieved the separation of the variables that we're working with in the problem. That's our key step. We just simply have to then evaluate this and start solving for y. So we have our two integrals. One of them is more straightforward. We end up with kx here. On this side, we have the ln of the absolute value of y, and we have two separate integrals here. It's worth noting that they both should have a plus c in principle. Let's call it plus c1 and plus c2. However, with what we always end up doing in this process, I'll show you the shortcut we take, which is effectively to move this to the other side. What that does is gives us a new constant, if you want to think of it that way. Call it capital C on the right-hand side. The idea is if we put the plus c from our integral just on the right-hand side, that's fine. If there was one on the left-hand side, we'd just move it to the right first and lump it in with that c value. It takes a little bit of adjustment, a little bit of experience to see how that will always work, and it's not a problem, but that's our process. Well, notice now we have a regular equation. And by regular, I mean non-differential. There's no derivatives anymore in our statement. So that means we just have a solve for y problem here. What we're going to do is try to get at the y value. To do that, we're going to need to take the ln of y and stick an e underneath that. If we're going to do that, we have to stick an e underneath the entire right-hand side as well. The purpose of doing that is that we get e and ln, those are inverses, and we get the absolute value of y equals e to the kx, and I'll just tidy that a bit. And notice the plus c in the exponent, it's often easier to write that as e to the c multiplying the e to the kx. We'll see why in a second. What I'd like to do is get rid of these absolute values, and notice this is always positive. We have two exponentials multiplied. We're going to do actually a little trick here that you'll see many times as you go through the practice problems for this section, and that's to define a new variable. We'll call it capital A, which is equal to this e to the c thing. That's one thing we can do. We can also say, well, if y was negative, when we take away the absolute values, we'll need to account for that. We're going to make that positive or negative as we need to. This feels a bit weird again at the start, but notice what we get in the end. We end up with y equals a e to the kx, a times e to the kx. That is exactly what we would expect for the equation we started with, which was dy dx equals ky. This was our exponential growth or decay equation. We've now solved it from first principles, and we end up with the not surprising result that we have an exponential growth or decay depending on what k is, and there's some possible scaling for an initial amount in this solution. It's also possible for y to start out negative. If we had a -5 here, we'd have a negative y values. That's totally fine. So this little kludge that we do here is going to be something that we repeat several times in the course just to get us back to the y values that could be negative and handling it carefully. If you have any questions about that, please ask in class or during office hours. As a last follow-up, we have a family of solutions, which is y equals a e to the kx. However, someone might also give us an initial value and say, let's take the one member of the family that starts at 10. Well, we've seen this kind of thing before. If y equals 10 and x equals 0, we sub that in. The y is on the left, it's there, equals a e to the k times 0, or just e to the 0. Of course, that's just 1. And so we get a equals 10. And so the specific solution, y equals 10 e to the kx, is the solution that we're looking for to satisfy both the differential equation and that initial condition, the starting point. That's our first exposure to an integration by separation of variables. Let's try it on a second example, a little more complex, to see if we can reinforce the process that we're using. Here we're asked to use the method of the separation of variables to solve this differential equation and find the particular solution that has an initial value of 0 when x is 0. Let's identify the process. We start with dr dx equals to r's plus 3. This time we're going to bring the dx up as we did before, but for the right-hand side, we're going to have to take this entire expression and put it in the denominator down here. And that'll be dr. The dx comes up, it stays by itself this time, and we throw an integral sign in front of both sides. The check that we make right now is that this has r's, but no x's, and this has x's, just the dx anyway, but the key thing is no r's in that side. With that in mind, we effectively integrate the number 1. If there's nothing showing, that will give us an x. On the left-hand side, it's a little more complicated. It'll be a ln of what we have there. But just be careful. If we were to differentiate this and go back, we would end up popping out a 2. We don't want that 2. So we would cancel it with a 1/2 multiplier. Scan across, what have you forgotten? The plus c on this side here. Again, you could put it here as well, but the next stage would be to move it to the right anyway. We just lump it all together, one constant on the right-hand side. Now our goal is to solve for the solution we want. This equation has r as the unknown, so that's what we're focusing on solving for. Bring the half up, we'll have ln 2r plus 3 equals 2x's plus 2c's. We want to hone in on the r again, so we'll take an e to the base of that entire expression there, e to this entire expression here as well. The e's and the ln's cancel. We end up with 2r plus 3 absolute value equals e to the 2x. And it's adding in the exponent, be very careful about that. That's the same as multiplying on the main line, so times e to the 2c. We then do the trick that we used last time. Let's make a new variable, call it a, that equals e to the 2c. But I also want to get rid of these absolute values, so if we need to, we'll put a negative sign in there, and that gives us 2r plus 3 equals e to the 2x, and then the e to the 2c is what we just replaced with a. Notice this is marginally more complicated than last time, but we're still just solving for r. 2r will equal a e to the 2x minus 3, bring the 3 over, and then we divide by 2. A over 2 e to the 2x minus 3 halves. And that is our general solution to the differential equation. This is a family of solutions. If we change a, we get a different formula. The last thing we might want to do is figure out what the a value is to match the initial condition, 0 and 0. So r equals 0 when x equals 0. That'll give 0 equals a over 2 e to the 0 minus 3 halves. Bring that over. We get 3 halves equals a over 2, or actually that's exactly what we want. You can solve for a if you like, but if you look at our expression, we actually have a over 2 anyway, so we're just going to keep that as 3 halves. So r equals a over 2 is 3 halves, e to the 2x minus 3 halves. That is our particular solution. And by particular, we mean the one specific solution that happens to go through 0, 0. So that's another complete example of separation of variables and using an initial condition to track down where that integration constant ends up. Notice we're using exactly what we did before with integration. We have the plus c as part of the integral process. It's when we manipulate the solution that we get to solve for this case r. Sometimes the plus c might turn into some other form. Here a multiplication, totally fine. The key thing is to remember that the plus c shows up when we integrate, and after that we just treat it like a regular variable or a regular constant.